Okay, so let's see how we can use the potential method to analyze this circuit. Yeah, so actually the current is I. So and actually this E is nothing but Em cosine omega dt. Okay, so in this case, suppose we assume this one to be the ground. So here is go up. So Em cosine omega dt equals, this is going down, going down, going down. So I times R and then plus VC plus VL. VL will be L di dt. L di dt. And then also we know that I equals C dV C dt. And then we can just plug in this one to here and also here. So here we will have yeah. So here we will have the first term will be R C dV C dt, and then plus VC plus LC d2 VC dt 2. And then this is still Em cosine omega dt. Here we can actually take the derivative of both sides. Take the derivative d dt on both sides. Then we will have here we have a negative Em omega d sine omega dt equals, take the derivative, will be like RC d2 VC dt 2 plus dVC dt plus LC d cube VC dt cube. Okay, so here we can actually multiply C on both sides, multiply by C, multiply by C, multiply by C, and then here we also multiply by C. So that this is actually I, this is actually I. So here we have, this one is I, we can put it at the back. So we have I, put it here. And then this one, we can just put it here, which is di dt plus and then RC. And then for this one, this is d2 I dt2, and then we have LC. We have LC. So on the left side is still minus C Em omega d sine omega dt. And then we can just divide LC on both sides. So we divide LC, divide LC, divide LC, divide LC. So it becomes negative Em omega d over L sine omega dt equals d2I dt2 plus R over L di dt plus 1 over LC times I. Okay, so in that case, this is a second order ODE with constant coefficient. And suppose we only consider the steady state. We only consider the steady state, which means when t tends to infinity, the complementary solution, which means the complementary solution will be tends to zero. Tends to zero. So we only consider the particular solution, but still we need to actually solve for this one. So actually, for the homogeneous, the characteristic equation, it is s squared plus as plus b equals 0. Here we have a to be r over l and b equals 1 over lc. And here we'll suppose s to be alpha plus j beta. Then in that also, okay, so then in that case, we will have I homogeneous solution to be exponential to alpha t a cosine beta t plus b sine of beta t. And here we should have alpha to be less than 0, which means that when t tends to infinity, this complementary solution, or I should make it like IC of t will tend to 0 when t tends to infinity. So we only consider the particular solution. And actually for the particular solution, we consider this term is a sinusoidal. So actually we just assume the particular solution to be d cosine omega dt plus e sine omega dt. Or we can simply regard it as r times cosine of omega dt plus phi, something like this. But yeah, you can just keep it in mind, we still use the d times cosine plus e times sine. And then we can just plug this one back to here. So in this case we have, we have a negative d omega d squared cosine omega dt minus e omega d squared sine omega dt, and then plus r over l, and then negative d omega d sine omega dt plus e omega d cosine omega dt, and then plus 1 over lc d cosine omega dt plus e sine omega dt. Okay, and then equals negative omega d em over l, and then sine omega dt. Okay, so quite complicated, but here we have 6 terms on the left side and then 1 term on the right side. So we can just collect the terms and then compare the coefficient. So for the cosine, it should be 0. So negative d omega squared plus r omega d over l e plus 1 over lc times d to be 0, which means that it includes this term to be here, and then this one times this one to be here, and then finally this one corresponds to this term. And then next is negative e omega d squared minus r omega d over l d plus 1 over LCE to be negative omega d em over L. So which means that this one is here, and then this one is here, and then this one is here, and then of course this one is this one. So in this case, we have two equations with two unknown, D and E, and then we can try to solve these two joint equation. Then finally, you will get D to be Em R over R squared plus omega dl minus 1 over omega dc quantity square. So this is the real part. This is the real part over the amplitude. Okay. Amplitude, yeah. And then E will be Em, and then negative omega dl minus 1 over omega dc, and then all over R squared plus omega dl minus 1 over omega dc square. So this will be the imaginary part. This is the imaginary part of the phasor. So if we really need to use the ODE to solve for the steady state response, the calculation will be so tedious. But making use the phasor, then many calculation can be simplified. So let's take a look at this sample problem, and then we can see how we can apply the phasor. Okay, so here it says R, CL, FD, EM are these values. What is the amplitude of the current phasor? So here A is R plus J. Z is R plus J omega L minus 1 over omega C. Okay, so R is 200 plus J, and then this FD is 60, so omega is 120 pi, and then L is 230 milli. Okay, then minus 1 over 120 pi, and then C is 15 times 10 to minus 6, like this. So this is the impedance of the RLC. Okay, so in this case, this is 200 minus J 90.13. Actually, we still use the ohm for the SI unit, even though it has the imaginary part, but still we use the ohm for the SI unit. Okay, so actually we just need to calculate this complex number, and then we can just calculate the phasor of the current to be Em over Z. This is Z. Okay, so Em is 36.0 over 200 minus J 90.13. Okay, so actually you need to just calculate the complex number. Yeah, maybe just by I'm not sure whether your calculator has this kind of operation, but nowadays I think many of the calculator has. Yeah. But if your calculator don't have, you can try to multiply the complex conjugate, which means multiply by the complex conjugate, which is 200 plus J 90.13 and then 200 plus j 90.13, like this. And then this is a squared minus b squared. So minus j squared will be minus 1. So this term will become 200 squared plus 90.13 squared. And then, yeah. Then you can find that, yeah, actually you don't really need to. And actually you can just calculate the I, absolute value of I will be 36.0 over 200 squared plus 90.13 squared. So in that case, you don't necessarily need to simplify this one. If only if you need to find the amplitude of this one. You just need to find the amplitude of the denominator and the denominator and the numerator, and then you divide them. Then this is the amplitude of the whole term. Okay, so this is 0.164a. So this is the amplitude of the current phasor. And then for part B, what is the phase of the current phasor? So phi is arctangent negative 90.13 over 200. So this is negative 24.3 degree. 24.3 degree. Or you can write it as a negative 0.424 radian. 424 radian. So you just divide it by 180 and then multiply by pi, then it will become the radian. Okay, so this is the phase. This is the phase. And of course, with the amplitude and the phase, you can write the I of t to be 0.164. And then cosine 120 pi t minus 0.424. So this is a time domain, the time domain one. If you really need to write the ODE, then it will become very tedious to find all these things. Okay, so far any questions? If not, we move on. So here we talk about the power in the AC circuit. Power in the AC circuit. So for the power, it is nothing but a P equals I square R, which is what we have learned before for resistor. And actually here it is a AC source, so the current is also an AC current, which means that if we try to plug in I equals absolute value of I, or actually it is like I sine of omega t dt minus phi. Okay, here the I can be a complex number rather than actually here it should be the absolute value, because we already write it as this is the amplitude, this is the phase, so yeah, this is already the absolute value. So when we try to plug this expression to here, we have this absolute of I square and then multiply by R and then sine square of this term. Okay, so this is the so-called the instantaneous power dissipated, which means that when you try to plug in t to be a specific value, let's say t equals 0, t equals 1 second, 2 seconds, then you can find the instantaneous power at that moment. And rather than that, we usually concern the average power rather than instantaneous power, because for this case, the instantaneous power is actually going up, down, something like that. So yeah, just say for this one, this is 0. This is 0. When this sine wave is equals to 1, then this is the maximum value, and then this is 0, and then this is -1. This is maximum again. Okay, so rather than that, we concern the average power. The average power. The average power is actually half of this one. So the point is that we try to integrate the power for a single period and then divide it by the period itself. So it makes it the average power. And actually these two terms, I square out, is irrelevant to the time t, So actually we only need to integrate this term from 0 to capital T. Capital T is the period. This is the period of the sinusoidal. Yeah, so you integrate this term, the sine square, from 0 to capital T, and then divide the whole term by t. Then it will be the average power. Or taking the integration is like the area of a period. Okay, so actually for sine square, it is nothing but half of 1 minus cosine to this term, which means that sine square of x equals half of 1 minus cosine of 2x. Yeah, if you still remember the trigonometry identity. Okay, so in that case, we can calculate this two term quickly. So for this one, the integration of 1 is t, and then you evaluate from 0 to t, so it becomes t. So this term becomes t, and this t will cancel each other. So finally, we have 1/2. And for this term, the integration becomes negative sign. But when you evaluate from 0 to t, when you plug in 0, which will be 1. When you plug in capital T, it is still not 1 because we have a fibers. Yeah, but actually, omega dt should be 2 pi, which means that it becomes sine of 2 pi minus phi minus sine of minus phi, something like that. And this one is becomes 0. So we have 1/2 for this integration, which makes that the average power is actually half of I square out. It's actually I square out this one. So this is the average power consumed by the resistor. Okay, so in that case, we can try to separate these two into the square root of 2, and then we try to deliver to this I. So this I is the amplitude. The absolute value of the I is the amplitude, and then if we divide it by square root of 2, it becomes the root mean square value. Because for this one we have an additional 2 here, but when we consider the sinusoidal wave and then we try to calculate their power, we usually will use the root mean square value, and in that case it becomes P average equals I root mean square times V root mean square. So which is what we familiar with, because when we consider the power, we can also write it as I of t times v of t, I times t times v of t. But here, but when we consider the p average, we have an additional 2 here, where we just use the amplitude. But here we try to consider is the root mean square value, which is the amplitude divided by square root of 2, and this is also the amplitude divided by square root of 2, and then it makes it like this without the factor of 2. So when we try to do something like the measurement or calculate something, you need to care about the root mean square value, just like what we have done in the lab for the magnetic induction. So some value is the root mean square value. So you need to be careful about the factor of square root of 2. Otherwise, it will be a 30% error, something like that. Okay, so here we also talk about the FH power dissipate can be written as I root mean square times R. So without the factor of 2, if we use the root mean square value. And then here it also mentioned that in a series RLC circuit, the average power P average will be like this. It will be I RMS times V RMS times cosine of theta because you can simply imagine just now we have V of t to be Em cosine omega dt, and then we have It to be Em all over Z. Z is the impedance, the R plus J omega L minus 1 over J omega Z, and then cosine omega dt minus phi. Okay, so here when we try to calculate the P average will be 1 over t and then 0 to t and then V of t times I of t dt. So in that case, when we try to multiply this one with this one, then you can use the cosine times cosine. It becomes, you add the term together. I'm not really sure. You can just make it like this one becomes cosine omega dt cosine phi plus sine omega dt sine phi. So when you try to multiply this one with this one, then you have cosine, and then with an additional cosine of phi factor. So here we have cosine of phi. But for this term, we have sine omega dt. We have cosine omega dt. It makes it like cosine x times sine of x is half of sine of 2x. If you just integrate this one for a period, then this one is 0. So we have an additional factor cosine of phi here for the RLC circuit. If the voltage, in this case the voltage and the current are not in phase, they have a phase shift of phi. So in that case, the P average, rather having I root mean square times V root mean square, we still need to multiply by this factor cosine of phi. So actually this one is this one. So here, let's take a look at a sample problem. So here it says a series RLC circuit driven with ERMS to be 120 volt at frequency FD contains a resistance R and inductance with impedance ZL to be J80 and capacitance with impedance ZZ to be negative J150. What are the power factor, cosine, phi, and phase constant of the circuit? Okay. So here we have a Z equals R plus J omega L minus 1 over J omega C. Okay, so this R is 200, and then plus J, and then omega is 120 pi as before, and then L or actually this one is this is already ZL, which means that this 80 is this omega L. So we have 80 here. And then for the ZZ is negative J over omega C. So this 1 over omega C is this negative 150. Negative 150. So which is 200 negative J70. So this is the impedance. This is the impedance of the RLC. And then it asks you what is the power factor. For the power factor, it is nothing but phi equals arctangent of 70 over 200. Or you can just take the negative sign. Take the negative sign. So this is nothing but negative 19.3 degree. 19.3 degree. So this is the imaginary part over the real part, and then take the arctangent will be the phi, and then so this is a negative 19.3 degree. So the power factor, which is cosine phi, so which is a cosine negative 19.3 degree. So this is 0.944. 0.944. Okay, so and for part B, what is the average power P average dissipate in the resistance? Okay, so here, so for Z is just now we have Z to be 200 minus J70, and then here we try to take the absolute value of Z, so which is 200 square plus 70 square, and then square root, which will be 211.9 ohm. So this is Z, absolute value of Z. And then here we have a P average to be ERMS square over absolute value of Z cosine phi. So actually ERMS is 120 and then square and then over 211.9, and then cosine of phi is 0.994. 0.944. So this case is 64.1 watt. 64.1 watt. So actually we make use of this one, and actually we have a VRMS will be IRMS times Z or like this. Yeah, actually should be like this, and then you try to plug in this one into here, then it becomes a P average equals VRMS square over absolute value of Z and then cosine of phi. So this is what we use here. And then for part C, it asks you what new capacitance C new is needed to maximize the P average if the other parameters of the circuit are not changed. Okay, so we would need a Z new. So the point here is we should try to make Z to be a real value. Make Z to be a real value. Because just now we have this to be the impedance to be R plus J omega L minus omega C. So if this is a complex number with imaginary part, then we cannot really maximize the output power. So the condition for having maximized P average is actually equivalent to having the resonant condition, which means that we should have omega L. I mean ZL plus ZZ to be 0. ZL plus ZZ to be 0, which means that here we should make everything unchanged except the ZZ. So which means that ZL is J80. Now we should make ZZ new to be negative J80. And then in that case, Z will be just Z will be out, which is 200. And in that case, we can maximize the output power. So in that case, we can actually calculate the C value, which is minus J80 equals minus J over 120 pi and then times C new. Then we can actually calculate the C new to be 33.2 microfarad. Any questions? Okay. So this is the last part of this chapter, which is about the transformer. So the transformer in Chinese is a 变压器. So it says a transformer assumed to be ideal is an iron core on which are wound a primary coil of NP turns and a secondary coil of NS turn. If the primary coil is connected across the AC generator, the primary and secondary voltage are related by this expression. So in that case, you can, actually it is what we have learned in chapter 30 about the mutual induction. Mutual induction in chapter 30, which is also the last part of that chapter. So here, so it says we have actually this expression. So here Vp is the root mean square value of the voltage for the primary coil, and then Np is the number of turns for the primary coil, and then so as Ns, Vs are the number of turn and the root mean square voltage for the secondary turn. So it will satisfy the condition of something like Vs over Vp equals Ns over Np, which means that the voltage of that coil will be proportional to the number of turn. So we can try to make the turn ratio to be a specific value, so that, for example, if we have a source here, if we have a source here, then we have more turns, or maybe in this figure, we have less turn for the primary coil, and then we have more turn for the secondary coil. Then in that case, Vs will be larger than Vp, which means that we can try to transform the voltage from a low voltage to a high voltage, or usually from the CEM, from the generator, the voltage might be as high as hundreds of kilovolt, and then it try to use some transformer to down convert the voltage to lower value, and then try to distribute to different places. And then finally, at the home end or at the socket, the voltage, the RMS voltage is 220 volt in Mattel. Okay, so actually it says for energy transfer, if the rate at which the generator transfer energy to the primary coil is equal to IPVP, this is the power. Actually, we also assume that the load is purely resistive, so IPVP, and then the rate at which the primary then transfer energy to the secondary coil is ISVS, and then we also assume that there is no loss and low energy loss in between. So we have the conservation of energy condition here, although practically it might not be that case, but if we really assume the energy is conserved, then we have this one is the power at the primary coil, this is the power for the secondary coil. They are equal to each other, and as much as we have V to be proportional to N to the number of coil, the current is inversely proportional. So you can see ISNS equals IPNP. Okay, so the current is inversely proportional to the number of turn. For the voltage, the amplitude of the voltage is proportional to the number of turn. Yeah. And in that case, you can see that if we try to divide Vs over Is, and then on the right side, Vp over Ip. But here we have this term over this term. So we take the reciprocal of this one and then multiply there. So we have ns over np quantity squared. So in this case, we can see for the primary coil, this is the impedance. This is the impedance. This is Vp over Ip is the impedance of the first coil. But with the number of turns different from 1, then the impedance or the secondary turn is multiplied by the ratio of the number of turns and then taking the square. So which is so-called the impedance transformation. This is so-called the impedance transformation. Impedance transformation. Okay, we transform, for example, from here, the impedance. Oh, this is Vp over Ip, and then this is Ns over Np. Here we have Ns to be larger than Np, so this term is larger than 1. This one is larger than 1, which means that the impedance here is lower. This is low impedance. Low impedance. This is high impedance. High impedance. High impedance. This is low impedance. So we can use the transformer to convert the impedance from the primary coil to the secondary coil. Okay. And this is so-called the R equivalent for the secondary. For the primary, which means that from the primary, the equivalent resistance we can see is actually Np over Ns squared times this R, because for the secondary coil, Vs over Is should be R, because this voltage and current are in series with this R. This is the loading, maybe a electrical device or whatever. But Vs over Is must be R for the secondary coil. But for the primary coil, it see a equivalent resistance to be Np over Ns quantity squared multiplied by this R. So it is so-called the impedance transformation. And here we have a sample problem regarding to this one. So it says a transformer on utility pole operate at Vp equals 8.5 kilovolt on the primary side and supply electrical energy to a number of nearby houses at Vs to be 120 volts. So but quantity being RMS value. And then assume the ideal step-down transformer, a purely resistive load and a power factor of a unity. So power factor equals to 1, which means that cosine of phi equals 1. There are no phase shift. Okay, what is the turn ratio at Np and S of the transformer? Okay, so Np over Ns is Vp over Vs. So which is 8,500 and then over 120. So the turn ratio is 70.8 for the first question. And then for the second one, the average weight of the energy consumption in the house set by the transformer is 78 kilowatt. What are the RMS current in the primary and secondary of the transformer? Okay, so in this case, we can calculate Is to be P average over Vs, so which is 78 times 10 to the third power over 120. So this current is 658. And then for IP, it is P average over Vp, so it is 78 times 10 to the third power over 8,500, which is 9.28. Okay, so these are the current, RMS current for the secondary coil and primary coil. And then finally, it asks you what is the resistive load Rs in the secondary coil and what is the corresponding resistive load Rp in the primary coil. So Rs is Vs over Is, so which is nothing but 120 over 650, which is 0.18 ohm. And then for Rp, which is Vp over Ip, which is 8.5 times 10 to the third power over 9.2, which is 926 ohm. So these are the values. So we only need some simple calculation for this one. But actually, this one actually tells you that why we need the high voltage power transfer, because which is something like VRMS. This is the source from the just say the CEM, and then it try to transfer all this power to your home, and then it will use the transformer to transfer it to just say 220 volt to your home, and then it of course needs some kind of turn ratio, NP over NP to NS. So for this case, this one we have a 920 ohm here, and yeah, the point here is that because from the electrical generator, it is far away from your home, which means that this wire is very, very long, which means that the resistance of this wire will be large. If it only use just the same voltage without the transformer, and then directly use a low voltage transfer to your home, then the intrinsic resistance will cause quite a lot of power loss due to the power transfer. And then okay, so and in that case, this is a 0.18 ohm. This is 0.18 ohm. This is still 0.18 ohm, but this one is long, and here if it is 926 ohm, then this intrinsic resistance might cause might cause only a small ratio of the power loss. But here, if it's just transfer the low voltage to your home, then the intrinsic resistance, the parasitic resistance here will cause a large loss comparing with this 0.18 ohm. So that's why we need the high voltage power transfer rather than low voltage power transfer. And I think that's all for today.